Hello operating systems people, this is Gabe Barmer, and today we're going to continue our discussion about memory protection by talking about page tables. And Penny is very wild right now and is going to probably help in the background. So, sometimes her help is not actually that helpful, but if you hear her, that's what's happening. So memory protection, as we talked about it, usually centered around this idea of a virtual address space, right? And this is simply the idea that each process has their independent namespace of addresses, and the same address in two different processes will not necessarily reference the same piece of actual memory. So every single virtual address space has a subset of physical memory mapped into it, and if that is a disjoint subset, then the two processes are isolated from each other. They cannot access each other's memory in any way, shape, or form. And we started talking about hardware support for virtual address spaces, and this all revolved around the idea that somehow we want to put into hardware a practical functionality for computing the function from virtual to physical. And of course, we said that this simple function is not quite it, because it's a function from virtual and which process is active to the physical memory. What we really want and what we did not get was the ability to have non-contiguous physical allocations mapping contiguously into virtual address spaces. And the idea here was effectively that if we have to allocate a whole bunch of memory, then we want to be able to do it discontiguously in physical memory so that we can avoid external fragmentation in that memory. So for instance, by using a buddy allocator to allocate allocations even that are not a power of 2 by calling the buddy allocator multiple times, right? And most importantly, the operating system needs to control this function. It needs to control the mapping of virtual to physical, thereby providing the requisite isolation within the system. So we're going to be talking about page tables and page-based memory protection today. So just to drive this example home, this is an example where we have allocated the physical memory contiguously that we mapped up into the virtual address space. Of course, we want to support lists, but we also want to be able to support multiple discontiguous physical allocations to be placed contiguously into a virtual address space. This means that effectively we could allocate even single pages to make contiguous allocations in a virtual address space. And that really removes the constraint that external fragmentation within physical memory really hurts us at all. And what you really want to think here is that what we're trying to do is support things like sbreak and memmap, right? So if they call sbreak with a value of x that isn't a power of 2, then we're probably going to want to call a buddy allocator multiple times with different request sizes to be able to satisfy that x request. But that means that the buddy allocator is most likely not going to give us those allocations contiguously. So paging is an attempt to be able to provide this physically non-contiguous allocations that can be mapped into arbitrary virtual addresses in a virtual address space. And it was created to actually make that function that maps between the virtual to the physical relatively fast to compute and usually done within hardware. So paging is a little bit of a compromise, as we'll see, between kind of the ability to do arbitrary allocations of arbitrary sizes and provide a fine-grained protection granularity and the efficiency of the actual hardware function for providing that protection within the MMU. So the whole idea behind paging is that we divide physical memory into frames that are all a power of 2, and different systems will provide different frame and page sizes. I'm going to be focusing on 4 kilobyte page and frame sizes. So physical memory is divided into these 4 kilobyte regions that are aligned on a 4 kilobyte boundary. Virtual memory is comparably divided into pages, which are the same size as the frames. And we now start to think of virtual memory not necessarily as which address are you accessing, but which page are you accessing. What this means now is that the kernel, when it's doing allocations to user level, needs to effectively trap track these frames. And that's why when we talked about the buddy allocator, the minimum allocation size was always 4 kilobytes. That's because that is the size of these frames that can be allocated up to user level. So when processes then request memory, we want to allocate a number of frames and be able to use the MMU and page tables to be able to map those frames up into the corresponding pages of the virtual address space. And the MMU then translates from these pages to frames. So how do we do this? We need to actually just start thinking about the pages in a little bit more technical of a way, and we want to break down every single address that we think about accessing. These are the pointers within C. We want to think about these pointers as being broken into 2 different components. One is the least significant bits, which is the offset into the page that that address is accessing, and the most significant bits are the page number, or the index of the page that we are accessing. So for instance, if we access a pointer that happens to have a P of 16 and a D of 2048, what that effectively means is that we are accessing the page at index 16 with an offset of around 2048 into that page, as indicated by the arrow, right? Now, a more concrete way to think about these page numbers and page offsets, really shown here, is that if we look at a 32-bit address, this is a bit field where each of the boxes is a bit in an address. If we look at the least significant bits, then a certain number of them designate the offset into the page that we're accessing, where the rest of them, the most significant values, designate the page number that we're accessing. And it really depends on the page size, how many bits are in each of these categories. So for instance, on a 32-bit x86 system, each of the pages, as we said, are 4 kilobytes, 4096 bytes, right? And 4096 bytes is 2 to the 12. So that means that the least significant 12 bits correspond to the page offset, and the most significant 20 bits correspond to the page number. So we can look at that generically for any architecture that has different page sizes. So imagine that we have a logical address space, a virtual address space of size 2 to the m. So on a 32-bit system, that's m is 32, and a page size of 2 to the n. So that would be 12 in the case where I have 4 kilobyte pages. We look at each address being broken down to the m-n most significant bits and the n least significant bits. And the MMU's job now is to take that P and that D, in addition to which process is actually active, and map that into a certain frame number and then add that offset onto the frame. So this is effectively what the MMU is doing now. What it's doing that's interesting is effectively trying to find this mapping between a page to a frame. And that can actually be done relatively efficiently. Before we go into how it's done, let's go over some examples. So in this example, let's imagine that we have very small pages, 8-byte pages. So 8 is 2 to the power 3, which means the least significant 3 bits represent the offset into each of the pages, and the most significant bits above that correspond to the page offset that we're referencing. So if we get a memory reference, a memory access to address 13, address 13 is 1101 in binary. So if we look at the least significant 3 bits, we know that the offset into the page is 5. And we know that the page number, the offset of the page, which page we're accessing, is 1. So because, of course, indices start at 0, we're on effectively the second page at an offset of 5 into that page. So the MMU should translate which page we're accessing, this page index 1, into a physical frame that is the actual physical memory that stores that page, and then we will offset 5 onto that physical frame to find the actual data that we're referencing. Now let's go through another example. If we try to access address 26, then we have the corresponding binary for that. So we want to look at the least significant 3 bits to figure out the offset into the page, and the more significant bits than that to figure out which page we're actually accessing. So if we look at that, we see 010 is an offset of 2 into the page, and the remaining most significant bits 11 means that we are accessing the page indexed 3, right? So the 4th page within our virtual address space, and you see that drawn on the virtual address space on the left. Now you should be able to write some C code to effectively do this separation between the offset into a page and which page we're actually accessing using just simple bitwise operations. You would definitely will see those operations in XV6, so you should go through that mental exercise. Okay, so we've talked about pages, and I've stated that they make a little bit of a trade-off, right? They are something that can be relatively efficiently implemented within an MMU because we aren't tracking every byte on the system. We're tracking these pages, which are a collection of bytes. So this allows us to have some granularity of the memory protection. The downside is that we can't protect memory less than the size of a page. So it's fundamentally limiting in that way, right? But because we're mapping from pages to frames, it means that we can have non-contiguous physical memory allocation because the frames that we use can be spread all across physical memory, and the MMU can make them appear contiguously in virtual pages. And as I talked about before, the MMU and this whole idea of kind of paging is just adding kind of a level of indirection to translate between the virtual and physical. So what do page tables look like? These are the implementation of the protection scheme that actually does this mapping between virtual and physical, between page and frame. So on the left, we have our virtual address space. On the right, we have our physical memory. In the middle, we have our page table. And our CPU, our abstract logical units, and our registers all are kind of working in terms of virtual addresses. And we see that we have broken up the blue address into P, the which page we're accessing, and D, the offset onto that page. And what we do is we essentially have the page table, which is a big array that has one entry in it per virtual page in a process. So it's just an array with a number of entries corresponding to the number of pages within our virtual address space. So when we find which page we are actually accessing, what we can do is say, okay, well, I know I'm accessing, for instance, the 5th page within my virtual address space. Let me look at the 5th entry in the page table. In this case, P looks up the entry that contains F, which is the frame that corresponds to that specific virtual page. And then we can correspond the actual address in physical memory that is being accessed by that load or store by concatenating together that F frame number with the offset into that frame that we're trying to access, and actually use that to access physical memory. So this is really, really cool because we're essentially adding this level of indirection through the page table that is doing our conversion from the page number into a frame number. And what controls that mapping between the two is essentially just an array that's laid out in normal memory. And the operating system actually controls this array. So it can rewrite its entries to either increase the memory that a virtual address space has access to, or remove entries to make it so that a process can no longer access a memory that it was able to previously. So let's go through a couple of examples of what this looks like. So here we have virtual memory on the left, physical memory on the right, and you can see that we have a number of virtual pages within virtual memory. Each of them corresponds to the entry in the page table that they point to. So the 0th index page within virtual memory, which is to say all of the addresses between 0 and 4096, is actually held in frame number 3 or index 3 in physical memory. The second page, the second virtual page in the virtual address space, from address 4096 up to 8190 whatever, 92 I guess, we look up its entry in the page table and we see that it is actually stored at offset 0 within physical memory. And you can see we have virtually contiguous pages that map to non-contiguous allocated physical memory, which is kind of one of the big superpowers of page tables. Now, page tables are used for many more things. What I haven't talked about yet is something that we've talked about many, many times in the class, which is the holes within virtual address spaces. The idea behind a hole in the virtual address space is that somehow there are addresses that you can access, but there's no memory behind those virtual addresses. And now we can see how that's done, because page tables don't just include the frame number that corresponds to a given virtual page. They also include a number of bits, and those bits include a valid or invalid bit, or sometimes usually called a present bit, and that denotes whether that entry, that virtual page actually has a valid mapping down to physical memory. So you can see that these first 4 entries in our address space have valid mappings at the corresponding physical frames. However, after that, none of the virtual pages are actually accessible. They're all marked with I as invalid, right? So this effectively means that if the process dereferences addresses within the first 4 pages of their virtual address space, within 4096 times 4 addresses, then you're going to access the corresponding physical frames. However, if you try to dereference an address above that, you're within the hole of inaccessible, or as we see now, invalid memory, and a page fault exception will happen. And as we've talked about many times before, this effectively gets translated into a segmentation fault by most Unix variants including Linux. But wait, there's more. Page tables provide even more operations than that, including access control bits. So not all memory can be read and written to, and we have the ability to have bits that tell us whether memory is readable, writable, and executable. Readable means that you can do loads from it, writable means that you can do stores from it, and executable means that you can try to execute it, right? So your instruction pointer can be set to it. So not all memory has all of these rights. So you can see in this example, the first 2 pages within the address space are marked as readable and executable. They probably contain the code of the process. The 3rd page is marked as read only. So it can't be executed, it can't be written to, it includes probably the constant global variables within your program. And then the 4th page is readable and writable. That probably includes all of the global data that, all the global variables that your program has created. And you can imagine that after that, after the 4th page is basically your heap pointer. So if you want to do dynamic allocations, the operating system can add to the page table by creating more valid mappings to additional frames. Set them as readable and writable because that's what the heap is, and at this point you are expanding the heap by just modifying the page table. Super cool. So we actually have an idea about how sbreak actually executes. This also is used for something that we talked about long ago in the class, around the 3rd week, 4th week, which is copy on write. So the idea behind copy on write is effectively that we can fork a process, and the parent and child have all of their memory set to read only. Well, now we know how that's done. We can actually just set the bit for readable for all of these pages that normally might be read-writable, right? So if the parent and the child have only readable mappings, which now means only updating their page table, not copying memory, right? Then when we do go to execute the parent and the child, then what happens? We'll get stores to read-only memory, which will cause an exception. a hardware exception that will start executing in the exception handler in the kernel, and we can add logic there that effectively can detect, oh, you know what, you're trying to store to a piece of memory that I made read-only because of copy on write. So what I want to do now is copy that page and then map that new copy into the child and make it read-writable there, and additionally change the mapping from read-only in the parent to be also read-write. So now we've copied the memory and provided two readable and writable mappings separately into the parent and the child. This is awesome. This is how we provide copy on write. Now you know the machinery behind it. In the vein of demystifying some of the things that we previously talked about in the class, here's shared memory. How do we do shared memory? Well, we just make it so that the page tables for two separate processes effectively map different virtual addresses in those different processes to the same physical frame. If you map to the same physical frame, then you have shared memory, because an access to either of those virtual ranges of shared memory will resolve to that same physical frame. So amazing, awesome, now we have shared memory as well. So I love this lecture because it kind of demystifies a lot of the stuff that I've left up as magic previously in the class. Hopefully you appreciate that as well. Penny does not. Penny just is overwhelmed by all the boxes. So she's a little tuckered, so, leave her to her commiserations. Okay, so how do we actually want to implement page tables? Page tables are actually just kept in main memory like any other data structure. They're often allocated with a buddy allocator because they're usually page aligned and power of 2 sized, which we'll see in a little bit. So they're just like any other data structure. The kernel allocates them normally and manages them normally. So you can actually see in XV6 where we're actually walking through the page table and accessing the entries in the page tables. You can add entries in page tables to add mappings to physical frames. You can remove them to remove memory from processes. The hardware does need to know at all points in time which page table is accessible, because while we're running, we're always executing on virtual addresses, which means we need a page table active at all points in time. So the PTBR, the page table base register, is set to hold the address of the currently active page table. Each process has a different page table. You can look through XV6. The CR3 register on x86-32 holds the address of the page table base. Now, the question for you is, do you have any recollection of which variable in XV6 gets written into CR3? Which variable holds the page tables within the system? Think about it for just a second, pause, come back. It's pagedir. Within the proc structure, there is the pagedir variable, and that actually holds the reference to the page table. So that's pretty cool. Now there's another connection that we created to previous homeworks. Okay. Writing to the PTBR and just generally accessing the PTBR at all is a privileged instruction. Think about for a second why that is. Pause, come back. Of course, this is because only the kernel should be able to actually switch the active page table. If a process were able to switch active page tables, then it might be able to access memory that it should not be able to, right? So this is, at the very least, it'll certainly hard crash the system. So you only want the kernel to be able to modify the PTBR and to control which address space, which virtual address space is active at any point in time. Here's a really hard question that I want you to ponder on significantly. The PTBR, does it hold a virtual or a physical address? Pause the video, come back. The PTBR holds a physical address. And I urge you to actually go into XV6 and print out the address of the pagedir register for an active process. It'll hold a relatively low value because it's actually holding a physical address. Now, the reason for this is that the PTBR is used to look up the page table that translates from virtual to physical addresses. If the PTBR itself held a virtual address pointing to the page table, then what would figure out physically where that page table is. The page table can't because we are supposed to use the PTBR to reference where the page table is. So we have a little bit of a circular logic problem here where we would need to use the page table to do the translation to find the page table, which we cannot do. So the PTBR always holds physical addresses. The next question is this: how many memory accesses for each load and store do we have now? And notice you would normally have one load and store if you're on a normal system without any of the stuff we've talked about this lecture, right? The memory access for the actual load or store itself. Pause, come back. So now we have two, right? We have one to access the page table and then one to do the load and store. So what page tables are doing is actually absolutely horrible, right? This is really bad. It's turning one memory access into two. Every single load and store that we do now becomes two memory accesses. And if you remember, I said before that memory accesses are one of the slowest things that we can do on modern systems. Memcopy is one of the slowest operations we can perform because it evicts a whole bunch of useful contents from the cache, which means that when we access it next, we're going to be accessing memory, which is an eternity from the processor's perspective, right? Accessing memory is at least 100 times slower than just doing computations, right? Okay, so we can't deal with that, right? Double the memory accesses for every load and store is not feasible, so we go to our ECE friends and we say, hey, what can you give us, right? Give us some sweet hardware that we can use to resolve this problem. And they say, okay, I got your back. I can give you this thing called a translation lookaside buffer, a TLB. A TLB is simply a cache. Now remember, a cache is a small piece of storage that stores a subset of some other larger amount of storage, usually in a faster to access form of storage, right? So you can access the cache relatively quickly. And that's exactly what the TLB is. It holds n page-to-frame mappings within the system, including holding all those bits, the readable, writable, executable, and valid or invalid bits, right? So it holds all of that. And it's implemented in content addressable memory or associative memory, and this is exceedingly fast and also exceedingly expensive memory, and it's implemented as part of the MMU, the memory management unit. And it's so expensive and it's so important because it actually needs to provide a translation between the virtual pages to the physical frames every single cycle. Every single load or store instruction, we need to ask the TLB, do you have a mapping? So the TLB is now being looked up for those mappings and not the page table, right? So this reduces the number of memory accesses on a load and store to just the one that you'd expect when we find our mapping in the TLB. So in the example that you see here, if we're looking up virtual address number or virtual page number 7, then we can iterate through the TLB and see that that second entry holds 7, and I know now that it maps to frame number 2. However, I just kind of lied to you a little bit. TLBs are a hardware construct, and hardware by default executes in parallel. You can have electricity flowing on 2 wires in parallel. Actually, sequentializing them takes a lot of effort. It's one of the grand accomplishments of humanity that we can actually serialize the chaos of hardware and of processors into something that gives us sequential execution. It's absolutely astounding. But by default, hardware is parallel. So this might seem strange for software people, but each of these entries in the TLB is searched at exactly the same time. So this is why TLB searches can be done in often less than a second, simply because when we look up page 7, we find 7 at the same time that we're looking at 16, 18, and 1. 7 happens to be the entry where we find it, and we find that that corresponds to frame number 2, right? Now, the big question for you is, what does the hardware do on a cache miss? Okay, so think about that for a second. Pause, come back. So on a cache miss within this TLB, that's when we go out to the page table. So we use the TLB by default to try to avoid accessing memory additional times other than just the load or store that's being conducted. And we only go out to the page table on the off case that we actually have a miss. And if we have a miss, then after the page table does the translation, then we also store that translation in the TLB, evicting some previously entry in there, so that that translation can be used for a future TLB lookup. So the question for you also is, how much do TLBs accelerate the system? Think about it, pause it, come back. In the case where we're always hitting the TLB, they accelerate the system an immense amount. 2 memory accesses turn into 1. However, it's almost never the case that if you have a cache, you're always going to hit in the TLB. So we often look at the hit rate of caches, which is the fraction of lookups that actually are satisfied by the cache, as one of the parameters of that cache. And in modern systems, TLBs have an immensely high lookup rate, or hit rate. It's usually on the order of 99%, if not significantly higher. So 99% of the time, we're actually avoiding going out to page tables and hitting in the TLB. So this is stellar, right? We're obviously accelerating the system quite a bit, and you'll realize later that we're accelerating it even more than this, because most modern page tables actually, to do a lookup in the page table, it takes 2 to 4 memory accesses. So the TLB is saving us from an immense amount of work. We'll find out even later that on virtualized systems, it can save you up to 20 memory accesses. So again, TLBs, kind of killer, right? TLBs take up a lot of power and a lot of space on chip because of this massive parallelism, but it's worth it for that reason. It's absolutely necessary. So let's look at TLBs in action. We've modified our diagram here to include a TLB. We have our P and D. The P is the frame that we're actually trying to access, and it will look that up in the TLB, which is the new block in the center here. And we see that within that TLB, the P entry does exist. So we'll look up the frame F and dump that into our actual address that we're using to access physical memory. However, if the TLB does not have the P that we're looking for, the page offset, in that case, we cannot use a TLB, so we need to go out to the page table. In that case, in this case, we find F, the mapping to the corresponding frame, and that will actually go 2 places. It'll go into our resulting address that we're using to look up, and we will add that mapping from P to F into the TLB, not shown here. Okay. So TLBs are kind of amazing. They're absolutely fantastic in many, many different ways. But they do cause some complexities that go beyond just the hardware cost of having the TLBs. And the question that I want you to ponder now is, if TLBs cause issues when switching between processes, would switching between processes complicate this notion of using a TLB in some way? Think about it for a second, pause, come back. Of course the answer is yes, right? If I'm asking a question like this, yeah, I mean, it's kind of a loaded question, right? Of course the answer is yes. But the question is, what complications do TLBs cause when we want to switch between virtual address spaces? Well, the first thing that you have to realize is that we are looking at a TLB that maintains mappings between virtual pages to physical frames. If we switch to another virtual address space, then all of those mappings that are held in the TLB are invalid because they are relevant for the previous process, not for the next process. So when we're switching between TLBs, that is when when we're switching between processes, between virtual address spaces, we need to flush the TLB. And flushing the TLB is an expensive operation. So we've talked before about kind of a hierarchy of different costs in the system, that we have function calls that are an order of magnitude faster than dispatching between threads in M-to-1 systems. And that's that's significantly faster than actually making a system call. And then if we want to switch between one-to-one threads, then we require system calls and dispatching and some kernel logic. So that's even more expensive. And then an order of magnitude more expensive than all of that is switching between processes, which is really just switching between threads. So it was unclear up until this point why it was more expensive to switch between processes. And now we see that if we need to flush the TLB, which is clear the TLB's contents, then that is the additional costs that we have to pay. And it's actually hard to put a number on how expensive that is, because how much of the TLB each of the processes involved was using actually goes into this cost. If two processes are using a very small amount of the TLB, then maybe it's not that much, because the cost of accessing memory, going out to page tables, and reading it into a TLB is relatively small. But if you access so much memory that you use your entire TLB cache, then it can be really quite expensive. Most modern systems, x86 was a laggard here, but most modern systems include something called address space IDs, ASIDs, and this is also called tagged TLBs. And what this does is it actually just, the TLB includes two things. It includes the virtual page that it's providing a translation for, and the address space ID, which is kind of like the process ID that virtual address is valid for. So it adds into the TLB lookup a little bit of complexity to only match the mappings that are relevant for a certain process, but it makes it so that we don't need to flush the TLB when we're switching between processes. Okay, now the question is, now that we understand what a TLB is, when a TLB has a miss, what happens? So there are actually two ways to kind of deal with this. There are hardware and software managed page tables. And the big question here is, does the hardware itself contain the logic for traversing a page table? So we talked about a page table as a big array. Does the hardware contain the logic to look up the corresponding entry in that array? As we learn that page tables get more complicated, does the hardware include the logic for traversing that? Therefore, we don't need to actually execute any software for doing those page table lookups. And that's the big polarizing question here. If we have hardware, software managed page tables, if the hardware includes that logic, then it will do lookups in the TLB, in the page table, and add it to the TLB on its own. However, if we get a TLB miss in a software managed system, then we get a translation exception that executes in the kernel. And that kernel handler that is activated on the translation exception must then go and figure out what entry it wants to add into the TLB. So now we define in software all of that logic for walking through the page table. So this is nice because now we can define page tables to have any shape that we want. We can implement them with any data structure. But it's really not nice because now our TLB miss going to the page tables is not just the one additional memory access for the page table, but a ton of additional memory accesses because we're executing software to do the translation. And there are additional complexities because when you're executing the translation exception, the translation fault handler, you always have to hit the TLB, right? Because if the translation fault handler triggers the translation fault handler, the system will typically reboot. So this is really hard to get right, and it always has a performance cost. All modern systems that I know of have hardware-driven page table traversal. Okay. So now let's actually get into kind of how you really implement page tables. I gave you an idea of how page tables work by thinking of page tables as an array, and I think that's a good mental model to have for how we might think about the logical data structure, but the actual implementation of the data structure can't really be what I said, right? It can't just be an array. And that's effectively because that array would have to have an entry in it per page within a virtual address space. And if you do the math, that is 4 megabytes of memory on a 32-bit system. 4 megabytes of contiguous, it must be contiguous, 4 megabytes of contiguous memory is horrible. That's a ton. You need one of these per process in the system, right? And on 64-bit systems, the size of the page tables would probably be more than the amount of physical memory that you have on the system. So this is not tenable. So there are a number of practical page table structures that are used in real systems. I'm going to talk about hierarchical page tables because they're pervasively used everywhere. Your laptop, your cell phone, everywhere. But there are additional things like hash page tables that use hash tables, inverted page tables that kind of flip hash table logic on its head. I'm not going to go into any of those, just hierarchical page tables. So again, we have this case where if we implement the page table as a big array, we're hosed because it takes a ton of memory, right? So all of the memory for all of the page tables, the operating system is not doing its job of providing applications the resources to do what they want. Operating systems are overhead. That much memory for page tables is a ton of overhead. So instead, what we do is we break page tables into a tree structure. It's actually one of my favorite data structures. It's called a radix trie, T-R-I-E, because, I don't know, British maybe. It's a really cool data structure that has immensely fast lookups that hardware can perform. And that's really important when you want a hardware page table walker. So a page table looks effectively like this. We have a top node, which is our outer page table node that the PTBR points to, at least to its physical address. And that outer page table node is essentially a relatively small node, usually that has 1024 items in it, so it's basically an array with 1024 items, and each of those items includes a physical address of a second level page table node, if there needs to be one. It could also be invalid. And then each of those second level page table nodes often has something like 1024 entries, and those include the actual physical frames that correspond to an address. Okay, so how do we figure out how to actually go through kind of these two levels of the page table? So the first thing that's most important is on the left, you see that our page number is broken down into two different sets of bits, P0 and P1. I told you before that the page number on 32-bit x86 is 20 bits large, so you can imagine it's relatively straightforward to split that into two separate 10-bit numbers, P0 and P1. And that also makes sense because 2 to the 10 is 1024, which is why each of these nodes has 1024 entries in each of its array. Okay, so what happens when we need to do a translation? The hardware will look up in the PTBR to find the outer page table node, and then it will look at P0, the most significant 10 bits of the address that we're trying to access, and look up that offset into the outer page table node. It will use the physical address in that entry to look up the next, the second level page table node. And then within that, it'll use the next most significant 10 bits in P0 to look up the offset into the actual frame. So it's just using different bits at different levels to actually offset into the nodes to find the next level of nodes. And when we finally reach the end in the second level page table nodes here, we see that we have the frame number that we can use to construct the final physical address that we're actually accessing. So this is effectively how hierarchical page tables work. This is the page table that we have in XV6 for x86 32. For x86 64, ARM64, we actually have 4 levels of the page table, which is why I said before that it kind of turns a TLB miss into 4 memory references in the page table, plus the 1 for the load and store. Again, re-emphasizing that TLBs really, really matter, right? Now, one thing that I want to point out here is that I said that we actually save memory by having hierarchical page tables over just having a big array. And you don't necessarily see that here because we just kind of are having a second level node for every single entry in the top level node. But what I want you to realize is that each of these entries in the outer page table node have a valid or invalid bit. And if it's valid, then that means that there is a valid second level page table node that is providing the translations for all of its constituent virtual addresses. But we can also set the invalid bit, which means that there is no second level page table node present. So we do not need to allocate the entire massive 4 megabytes of the page table. Instead, we just need to allocate page table nodes, well, of course the outer node, but then we only need to allocate second level page table nodes for the addresses where there are actually valid mappings. So this is why we always talked about the hole in the virtual address space as somehow saving memory, right? We didn't map memory up into a process, because effectively the second level page table nodes are not allocated, and at the outer page table node, all of those mappings are invalid. So wherever we have holes in our virtual address space, we don't even need the second level page table nodes to correspond to them. So just a little bit of a summary for the numbers that we have. In a 32-bit virtual address space, we have 4 kilobyte pages, which is 2 to the 12, which means our offset into each of the pages is the least significant 12 bits. That leaves the most significant 20 bits, and we break that into P0 and P1 to index into the outer page table and second level page table nodes. And we know that the size of P0 and P1 sums up to 20, and in our specific case of x86 32, each of them is 10 bits. But as I said, on 64-bit x86, we have 4 levels, and each of those levels has 9 bits each. So this doesn't always save memory. There is one case where it does not. Think about it, pause, come back. So this actually doesn't save memory in the case where we actually need a second level page table node for every virtual address because the virtual address space is so heavily populated. Because in that case, we have 4 megabytes of second level nodes, and then in addition, we have the outer page table. So we are actually using 1 page more, 496 bytes for the outer page table node, in addition to what we would use for just the big array for just the single level page table. But it's important to note that each of those nodes in the page table don't need to be contiguous. So even if we are using a slightly more memory in that case, we don't really care, because being able to allocate them non-contiguously is a really big benefit. Okay, so the last thing that I want to talk about is hardware virtualization and how hardware actually helps us provide an abstraction of virtual machines. And the idea here is effectively that a VM thinks that it has page tables, right? A virtual machine thinks that it has its own kernel mode. It thinks that it has its own page tables. It thinks that it's mapping from virtual addresses to physical addresses. But of course, it can't be, because there needs to be a hypervisor or a VMM executing in the real kernel mode of the hardware that is managing physical memory. So we need some sort of a change of terminology here. We need a new address space or namespace within the system. We have virtual memory, we have physical memory, and we say that physical memory is within the virtual machine, but then we have machine physical memory as well, that is actually the real physical memory on the machine, right? That the VMM or the hypervisor manages. So how this works is that for this additional namespace, we have an additional page table effectively. So we have a page table executing within each of the virtual machines, but then an additional page table executing within the hypervisor, mapping between physical addresses of the virtual machine to machine physical addresses within the real machine, right, within the hypervisor. So we call this nested page tables because you can kind of think of these, you have one page table nested within the other, right? Now, this is a really hard question. I'd like you to think of how many memory accesses it would take if we were using x86-32 and doing nested page tables. Go ahead and pause, think about it. It's actually not the summation of the two. So it's not like, okay, I would have 2 extra memory accesses in the guest, 2 extra memory accesses in the hypervisor. It's not that. It's actually, you have a quadratic increase of the number of memory accesses. So let's see why. So in this diagram, you have the guest virtual machine executing its kernel, thinking it's modifying the page tables of the system and thinking it's referencing physical memory. And of course it is, but the hypervisor or the real kernel of the system is managing the machine physical, the real physical memory within the system, right? And it has its own page tables, one per virtual machine. So that means it has essentially a virtual machine PTBR that says which virtual machine is active at any point in time, which virtual machine's physical memory is active, and this is used to translate requests to the physical memory within the virtual machine. Now, the thing to realize that it's actually really hard to kind of just think about naively is that when we have a load or store, it misses the TLB, then it's going to need to access, of course, the outer page table within the virtual machine. But that requires a load from that page table. That load within the outer page table node itself can cause needs to be translated from physical to machine physical addresses. So that one access to the outer node can actually cause multiple memory accesses, 2 memory accesses if we have a 2-level hierarchical page table within the hypervisor. So we have 3 memory accesses just for kind of accessing that outer page table node. And we figure out which second level page table node to use, but that itself, when we do a load from it, requires translation from within the hypervisor's nested page tables. So that in total causes another 3 memory accesses. And then finally, when we go and do the final load or store itself, that is to physical memory, which can cause an additional couple of memory accesses within the hypervisor. So in total, this causes a quadratic increase in the number of memory accesses within the system for each TLB miss. So you start to see TLBs are not just kind of like a nice thing, they are an essential thing, because this many page table accesses is a huge number, and it's hugely expensive. So correspondingly, we saw in around 2005 that we had like 128 TLB entries on a lot of systems. And around that time is when people started pushing into hardware this notion of hardware virtualization extensions or hardware acceleration for virtual machines, including nested or extended page tables. And now we're in 2020 when we have 4096 entries in our TLB. Simply because missing the TLB becomes immensely expensive, so we want to make sure it's as large as it can be to hold the entire working set of your applications. Now, this wasn't the only reason that we expanded TLBs. Also, working sets, the amount of memory accessed within a short amount of time by applications, increased significantly. But this was one reason. Okay. So we've been talking about memory protection, and this is one of my favorite parts of this class. It's the foundation for all the security and reliability that we seek within system, and it's an interesting case study in hardware-software co-design, because the hardware is accessing the same page tables that software is setting up, which is really cool. So we looked at many means of providing hardware protection, focusing, of course, on page tables, which require new caches to accelerate them, the TLB. We also talked briefly about software protection and how it requires inline checks into your code to make sure that you're accessing data that you should, which has a performance impact. And all of these things are used in different domains, and it's very complex. We've gone through a lot of technical details, but it's absolutely necessary in modern systems to have that protection, to have that security. So thank you very much. Hope you enjoyed this. We'll see you all soon.